Alright, so we got a couple formulas to talk about. The main formula is depicted here. If you have the union of A and B, you can see, well, if we wanted to add up all of the probabilities in this space, we would add the A and the B, but then we would have counted that center intersection in both cases. So we have to subtract off that intersection because of the double counting. So the first formula, now how we calculate this intersection, that gets a little bit trickier. So there's two types of probability. There is an independent probability, like your coin flips and your dice and your spinners, things that are based on the geometries or very predictable theoretical probabilities. And then we have a second category called dependent, and that's a different category. So I'm gonna wait to discuss that. Let's talk about, well, how would you calculate the probability of intersection of two events, A and B, if things are independent. So let's write that one down first. That means that one event happening, like say you get heads this coin flip, that doesn't change things in the future. So they don't affect each other. And to figure that out, that's most of your experience in probability thus far has been doing independent probabilities where you multiply the branches of a tree in a tree diagram. And so if you want to figure out the intersection probability of A and B, you would just multiply them together. So coin flip, say for example, probability heads, you would just multiply 50% times 50%, and that probability is 25%. Okay, that's for independent events. Now, oftentimes things do influence each other. Like, if the probability of rain is high, then the probability that I'm going to bring an umbrella or dress appropriately, that changes. And most things that humans do seem to be very dependent on other probabilities. And so we have a dependent category also. Okay, so one event's outcome affects, with an A because it's a verb, the probability of another event's probability. And the way we calculate this, probability A intersection B, is probability A times probability. So A happens, and then that changes the likelihood of event B. And so there's a symbol that we need to use, although the actual calculation is similar. It's a multiplication of two percentages. And so the second one is going to be written as this, probability B given A. Okay, so A happened first, and then that changed, the B is no longer its same probability. It changes to a new probability, and this is the symbol that shows its probability has changed. And so do a quick example here. Example, 52 card deck. Probability of getting, say, queen, there's 4 out of 52. Okay, now if you wanted probability of two queens, queen, queen, a pair of queens, then you wouldn't, like before, just multiply 4 50-seconds times itself, because once you pick the first one and supposing you don't put it back, that changes the probability, and this is the symbol that shows that probability has been changed. And so 4 50-seconds times 3 51st, getting screen here, and then we would just multiply those to figure out what the actual amount is. And let's go ahead and finish that and do a 0045. So pretty slim chance if you just pick two cards out of the deck that it'll be that combination. Okay, so there's a basic difference, and now the value of this is oftentimes you don't know if the probability is independent or dependent, and this calculation will tell you which one you're dealing with. And so frequently in the homework set, you have maybe 3 out of the 4 of these pieces of information, and you have to solve for what's missing. Now, there's sort of a test here. If your probability ends up calculating simply, you multiply the numbers and then you get the intersection, that means you're dealing with an independent situation. If not, then that would suggest that the two events that are in question, they affect each other. So we'll do some examples of that. Alright, so while I was editing this, I thought of another example for a dependent probability, something that might further explain how dependent probabilities work. So let's say, just use the example of your common breakfast item. In our house, we eat a lot of waffles, and so if my first son, Teddy, if he eats a waffle, which is maybe a 50-50 chance he'll want waffles, then my other son, Arthur, it will be influenced by Teddy's decision. And so let's make our two events whether or not my first son eats a waffle or my second son eats a waffle. So I'm going to go ahead and write those down. Okay, so I'm just going to say for either son, 50-50 chance. However, if Teddy happens to want a waffle, the probability that Arthur is going to want a waffle changes. It's no longer going to be 50%. It goes way up. In fact, it's almost guaranteed. So there's a symbol for this. The symbol that suggests this is probability now that Arthur eats a waffle, given, and this is a given that symbol, Teddy eats a waffle. Now it's almost guaranteed 90% chance. Okay, so this is dependent probability. Is one thing's outcome affects the probability of what's to come. And if we make a tree diagram of this, this is what the tree diagram looks like. Okay, so the first split, 50-50 chance Teddy eats a waffle. If he doesn't, then Arthur's chance is 50-50 still. However, if he does, that's the probability that he does, given that A happened, which was Teddy eats a waffle. Then it changes, so 0.9, 0.1. And you still do the same calculations. It's just 0.5 times 0.9, 0.45 for this particular pathway, this combination to happen. The only thing that is maybe new to you this year is we're going to use this symbol to suggest, to reference this particular branch of the entire tree diagram. So that's the new part for you. So probability, Teddy has a waffle and Arthur has a waffle, is 45% chance, and what we did, we took 50% and multiplied it by the part of the tree diagram that followed Teddy eating a waffle, which was Arthur eats a waffle given Teddy ate a waffle, 0.9.